Empty space. Nothing. The void. Remove every atom, every photon, every last shred of matter and energy, and what remains should be pure absence. Absolute zero. But physics says otherwise. The void refuses to be empty. Quantum mechanics dictates that even when you strip the universe down to nothing, something remains. A seething ocean of energy that creates particles from thin air, pushes metal plates together across a vacuum, and may explain why. Black holes glow. What fills the space when everything is removed? Why does emptiness have weight? What happens when observers accelerate through nothingness and suddenly see heat? Classical physics says they should feel nothing, no force whatsoever. But Casimir calculated that the vacuum itself would push these plates together, not weakly, not theoretically, measurably. The force exists because of what quantum field theory calls virtual particles, fleeting fluctuations in the electromagnetic field that pop into existence and vanish in fractions of a second. Between the plates, only certain wavelengths of these virtual photons can exist. Outside the plates, all wavelengths swarm freely. This difference in energy density creates pressure. The plates move. The result matches Casimir's mathematics to within 5% experimental uncertainty. The vacuum pushed. Physics Today reported in October 2025 that this force reaches a few hundred piconewtons when plates sit 100 nanometers apart. Tiny, but real. Metal moving because of nothing. The Casimir Effect became the first direct experimental proof that quantum vacuum fluctuations have physical consequences. If you value documented quantum mechanics and experimental physics like this, subscribe. It's the best way to support our work. Also, comment from which city you're hearing this from. This script is researched and factual, using sources from peer-reviewed publications in Physics Today, published October 2025, covering recent Casimir Effect studies, and Nature Journal's November 2011 paper by Christopher Wilson and team at Chalmers University, documenting the first dynamical Casimir Effect observation in superconducting circuits. Now back to the information. Mirror moving at relativistic speeds by changing the effective length of a microwave resonator. The prediction. If a mirror moves fast enough through the quantum vacuum, virtual photon pairs get separated before they can annihilate. One photon escapes, the other falls behind. Virtual particles become real. The vacuum spits out actual photons. Microwave photons emerge from the vacuum. Photons that weren't there before, created by the changing boundary conditions of the resonator. MIT Technology Review on May 26, 2011 called it the first experimental observation of the dynamical Casimir Effect. But the Casimir Effect and its dynamical cousin aren't isolated curiosities. They're manifestations of a deeper reality discovered in 1947 by Willis Lamb and Robert Rutherford. They measured the energy levels of hydrogen atoms using microwave spectroscopy. According to Paul Dirac's relativistic quantum equation from 1928, two specific energy states of the hydrogen electron, the two s1/2 and two p1/2, levels should have identical energy. Dirac's mathematics was precise. His prediction was wrong. Hans Bethe calculated the answer in 1947 on a train ride back from the Shelter Island Conference to Cornell University. The vacuum itself was interacting with the electron. Virtual photons, the same fluctuations behind the Casimir Effect, surround the electron constantly, causing it to jiggle. This jiggling changes the electron's energy depending on how close it gets to the nucleus. So state electrons penetrate close to the proton more often than p-state electrons. They experience more vacuum interactions. Their energy shifts upward by 27 megahertz from vacuum polarization effects, where virtual electron-positron pairs briefly materialize in the proton's electric field, screening its charge. Megahertz, according to experiments published in Physical Review Letters in 1998. Theory predicts 1057.864 megahertz plus or minus 0.014 megahertz. Agreement to within 1 part in 50,000. The vacuum fluctuations are real. They shift atomic spectra. They're measurable. Quantum electrodynamics, the theory describing how light and matter interact through virtual particles, became one of the most precisely tested theories in all of physics because of this shift. Julian Schwinger, Richard Feynman, Shinichiro Tominaga, and Freeman Dyson developed the full mathematical framework. Feynman won the Nobel Prize in 1965. Lamb won in 1955. The vacuum stopped being nothing. 1974. Stephen Hawking publishes a shocking calculation about black holes. Black holes, by definition, trap everything, not even light escapes. But Hawking applies quantum field theory near the event horizon, the boundary where escape becomes impossible. Virtual particle pairs constantly form near this boundary. Normally, they annihilate instantly. But at the horizon, one particle can fall into the black hole while its partner escapes to infinity. The escaping particle becomes real. The infalling particle carries negative energy relative to a distant observer. This negative energy reduces the black hole's mass. The black hole evaporates. Slowly. A black hole with the mass of our sun would take 10 to the 67th years to evaporate, vastly longer than the current age of the universe, which sits at roughly 14 billion years. But micro black holes would evaporate quickly, ending in bursts of gamma rays. But in 2015, Jeff Steinhauer at the Technion Israel Institute of Technology in Haifa created an analog black hole using a Bose-Einstein condensate, a cloud of ultra-cold atoms behaving as a single quantum entity. Sound waves in this condensate mimic light near a black hole. Where the flow speed exceeds the speed of sound, an acoustic event horizon forms. Steinhauer measured correlations between phonons, sound particles, on opposite sides of this horizon, precisely matching the prediction for Hawking radiation pairs. The paper appeared in Nature Physics, requiring 6 days of continuous measurement. They measured wave amplitudes and confirmed the theoretical prediction for the ratio of ingoing to outgoing waves, a ratio that depends on the effective temperature at the horizon. Scholarpedia published these results in December 2011, noting they achieved statistical agreement with theory within error bars. These aren't real black holes, they're analogs. But the mathematics governing the vacuum fluctuations is identical. The quantum vacuum responds to horizons, boundaries where propagation changes character. Whether that boundary comes from gravity or fluid flow doesn't matter to the underlying quantum field. Empty. But accelerate through that same vacuum, and it transforms into a thermal bath. The en-route temperature depends on acceleration. The formula gives roughly 4.06 times 10 to the negative 21st. Kelvin times acceleration in meters per second squared. To reach 1, Kelvin requires an acceleration of 2.47 times 10 to the 20th meters per second squared. An absurdly high value, far beyond current. Technology. Lynch modeled the positrons as Unruh DeWitt detectors and calculated the radiation spectrum they should emit if the Unruh effect is real. The spectrum should be thermalized at the Fulling-Davies Unruh temperature, corresponding to the acceleration. Lynch's team stated, this provides experimental evidence for the Unruh effect, the first observation connecting acceleration, vacuum fluctuations, and thermalization. The experiment ran at CERN in the NA63 collaboration measuring quantum radiation reaction in aligned crystals. Independent confirmation came from European Physical Journal C in May 2024, analyzing thermal photon emission from accelerated electrons. Again, finding consistency with Unruh's prediction. The vacuum state, what an inertial observer calls empty space, isn't the same for an accelerating observer. Acceleration changes, which combinations of field oscillations count as particles versus antiparticles. This is formalized through Bogoliubov transformations, mathematical operations that relate particle definitions in different reference frames. Quantum mechanics forbids any system from sitting perfectly still at zero energy. The Heisenberg Uncertainty Principle demands that position and momentum cannot both be precisely zero. A particle confined in space must have momentum fluctuations. Those fluctuations mean kinetic energy. Even at absolute zero temperature, negative 273.15 degrees Celsius, atoms in a solid still vibrate. Liquid helium doesn't freeze under atmospheric pressure at any temperature because its zero-point energy keeps atoms moving. Classically, a spring at rest has zero energy. Quantum mechanically, the ground state energy is 1/2 times Planck's constant times frequency. Always positive, never zero. Sum this over all points in space, all frequencies, all field types. The result, infinite energy density. This is the vacuum energy. The calculations only make sense up to a certain energy cutoff. Above the cutoff, new physics takes over. Using the Planck energy as a cutoff gives a vacuum energy density around 10 to the 115 times the observed energy density of the universe. This is the cosmological constant problem, the worst mismatch between theory and observation in all of physics. Jérôme Martin of Institut d'Astrophysique de Paris in 2012 estimated the discrepancy at 55 orders of magnitude when using dimensional regularization, or 120 orders of magnitude if using Planck scale cutoffs with simpler schemes. In 1998, observations of distant type Ia supernovae by Saul Perlmutter, Brian Schmidt, and Adam Rees showed the universe's expansion is accelerating. This earned them the Nobel Prize in 2011. The acceleration requires something pushing space apart. That something is called dark energy, and it makes up roughly 68% of the total energy content of the universe, according to Planck satellite measurements, published in 2018. The simplest explanation for dark energy is a cosmological constant, a constant energy density filling all of space. That constant is the vacuum energy. Quantum field theory predicts values tens or hundreds of orders of magnitude larger. Something cancels almost all the vacuum energy, leaving only a tiny residue. No one knows what. No symmetry in physics requires this cancellation. No mechanism explains it. Proposals exist. Supersymmetry, extra dimensions, the anthropic principle in a multiverse, but none are confirmed. Yakov Zeldovich pointed out the problem in 1967. 58 years later, it remains unsolved. Each symmetry-breaking phase transition in the early universe as temperature dropped contributed more energy. Electroweak symmetry breaking at 100 giga-electron volts adds a contribution around 10 to the negative 67 in Planck units. Quantum chromodynamics, chiral symmetry breaking at 300 megaelectron volts adds 10 to the negative 79. The standard model of particle physics, our most successful description of fundamental forces, predicts a vacuum energy density that should curve the universe into a region smaller than the solar system. It doesn't. The universe is vast, flat, expanding. Magnetic moment of the electron all require vacuum fluctuations. These aren't theoretical conveniences. They're measured. The electron's magnetic moment matches quantum electrodynamics predictions to better than 1 part in 10 billion, according to experiments by Gerald Gabriels published in Physical Review Letters in 2006. That precision requires including contributions from virtual particle loops, electrons emitting and reabsorbing, photons, virtual electron-positron pairs briefly forming and vanishing, even heavier particles like muons and tau leptons contributing through quantum corrections. Energy density? The cosmological constant problem might not arise. Others, like George Ellis, propose modifications to general relativity where vacuum contributions simply don't couple to gravity. These ideas remain speculative. The consensus view is that vacuum energy should gravitate according to standard general relativity, and the mismatch between prediction and observation reflects deep ignorance about quantum gravity or the early universe. Meanwhile, experiments continue pushing boundaries. In March 2013, Proceedings of the National Academy of Sciences published an experiment demonstrating the dynamical Casimir Effect in a Josephson metamaterial, an array of superconducting quantum interference devices arranged to simulate a rapidly oscillating boundary. Photons emerged from the vacuum as predicted. July 2019 brought another confirmation in Optics Express, showing optical dynamical Casimir Effect in dispersion oscillating fiber, where the fiber's refractive index oscillates in time, mimicking a moving mirror. Each experiment adds evidence that vacuum fluctuations are not mathematical artifacts. They have consequences. Quantum mechanics says the atom couples to the electromagnetic field. Even in vacuum, the field has 0-point fluctuations. These fluctuations trigger the transition. Paul Dirac showed in 1927 that the rate of spontaneous emission depends on vacuum fluctuations to get started. Without the vacuum field, an excited atom in a perfect cavity with walls spaced such that the photon wavelength doesn't fit couldn't emit at all. Prediction confirmed by cavity quantum electrodynamics experiments, suppressing emission rates by factors of 100 or more when atoms sit in carefully designed cavities. Information? Paradox. If Hawking radiation from a black hole is purely thermal, random, it carries no information about what fell into the black hole. Quantum mechanics forbids information destruction. Paradox. Wilczek's work suggests information escapes through correlations in the emitted particles, encoded in the quantum entanglement between Hawking photons and their partners that fell into the black hole. The vacuum isn't a passive backdrop. It's a participant in information transfer. Published in Nature Physics, the paper required sophisticated analysis, extracting signal from noise over thousands of experimental runs. The Fourier transform of these correlations measures the entanglement strength. At low frequencies, the entanglement approaches its maximum quantum mechanical value. The vacuum produces correlated pairs. The Casimir force between two parallel conducting plates of area 1 square meters separated by distance L in meters is roughly negative pi squared times Planck's constant times speed of light divided by 240 times L to the 4th power, measured in newtons. At 1 micrometer separation, that's approximately 1/10,000th of a newton. Tiny but measurable with atomic force microscopes. Decrease the separation to 100 nanometers, and the force increases by a factor of 10,000 to roughly 100th of a newton. At 10 nanometers, it reaches 10 newtons, strong enough to feel. Micro-electromechanical systems, MEMS devices, must account for Casimir forces at these scales or components stick together unexpectedly, a phenomenon engineers call stiction. The Lamb shift in hydrogen, 1057.864 megahertz plus or minus 0.014 megahertz. For the 2 S 1/2 minus 2 P 1/2 splitting. Break this down. The vacuum fluctuation contribution shifts the 2 S 1/2 level upward by approximately 1085 megahertz. Vacuum polarization, virtual electron-positron pairs, shifts it downward by 27 megahertz. Smaller corrections from finite nuclear size and reduced mass effects subtract roughly 1 megahertz. Net shift, 1057 megahertz. This tiny shift revolutionized quantum electrodynamics. Before Bethé's calculation, physicists didn't fully understand how to handle the infinities that appeared in quantum field theory. Bethé's insight Separate the infinite self-energy of a free electron from the finite energy shift of a bound electron. The difference is measurable. This was the first successful renormalization in quantum field theory. Meters per second squared. Plug this into Unruh's formula. The Hawking temperature is 6 times 10 to the negative 8th Kelvin. The corresponding thermal radiation spectrum peaks at a wavelength around 100 kilometers. Detecting this against the cosmic microwave background at 2.7 Kelvin is hopeless. But a micro-black hole of 1 billion kilograms, roughly the mass of a small mountain, has a temperature of 120 million Kelvin and radiates mostly gamma rays. It would evaporate in 2.6 seconds. The Unruh effect temperature, 4.06 times 10 to the negative 21st. Kelvin per meter per second squared of acceleration. An electron in a laser field with intensity 10 to the 25 watts per square centimeter experiences acceleration around 10 to the 26 meters per second squared. Unruh temperature, 4,000 Kelvin. Hot enough to ionize atoms, hot enough to change atomic spectra measurably. Experiments proposed in European Physical Journal C in May 2024 suggest using high-intensity lasers to accelerate electrons and measuring spectral changes in atoms attached to those electrons. Current lasers reach 10 to the 23 watts per square centimeter. Intensity 10 to the 25 requires next-generation facilities like the extreme light infrastructure in Romania. The zero-point energy of a single quantum harmonic oscillator with frequency omega is 1/2 times Planck's constant times omega. For an electromagnetic field mode with wavelength 1 micrometer, infrared light, the frequency is 3 times 10 to the 14 hertz. Zero-point energy, 1 times 10 to the negative 19 joules, equivalent to 0.6 millielectron volts. Not much, but space contains infinite modes. Integrate over all wavelengths from 0 to infinity. The energy diverges. Physics saves itself by imposing a cutoff at high energies where the theory breaks down. Using Planck length, 1.6 times 10 to the negative 35 meters, as the cutoff gives a vacuum energy density of 2 times 10 to the 113 joules per cubic meter. Compared to the critical density needed to make the universe spatially flat, 9.5 times 10 to the negative 10 joules per cubic meter. The ratio, 2 times 10 to the 122. This is the cosmological constant problem in its starkest form. But supersymmetry, if it exists, is broken. The superpartners are heavier than known particles. The Large Hadron Collider found no superpartners up to energies of several tera electron volts. Broken supersymmetry gives contributions comparable to standard model fields, not zero. Another proposal? Unimodular gravity, where the cosmological constant emerges as an integration constant rather than a dynamical field contribution. In this framework, vacuum energy doesn't gravitate because the theory treats space-time volumes separately from matter dynamics. Unimodular gravity makes testable predictions about how vacuum energy couples to gravity, but experiments haven't yet distinguished it from standard general relativity. Formation. Too large a cosmological constant causes runaway expansion before galaxies form. Too large a negative causes immediate collapse. The observed value sits in a narrow window permitting stars, planets, and life. Critics dislike this explanation because it's not predictive. It explains one number by invoking infinitely many unobservable universes. In May 2011, Christopher Wilson's team at Chalmers published in Nature the detection of dynamical Casimir photons. They used a superconducting waveguide with a squid acting as a tunable boundary. By modulating the squid at 11 gigahertz, twice the cavity's fundamental resonance, they excited the vacuum into producing photon pairs at the resonance frequency. They detected microwaves where none existed before. The experiment required temperatures below 0.05 Kelvin to suppress thermal photons. Signal processing isolated vacuum-produced photons from noise. The paper reported several hundred photons produced per modulation cycle, far above background levels. Published in Proceedings of National Academy of Sciences, they measured photon production rates consistent with theoretical predictions, confirming that time-modulated boundaries produce real particles from vacuum fluctuations. Their setup achieved modulation frequencies up to 10 gigahertz. Higher frequencies produce more photons but require faster electronics. Researchers created optical fibers where the refractive index oscillates in time through nonlinear effects. As a pump pulse travels through the fiber, it modulates the vacuum field. The oscillating index mimics a moving mirror. They measured photon pairs emerging from the fiber, photons created from vacuum fluctuations by the time-varying boundary conditions. Published in Optics Express, the paper showed spectral signatures matching dynamical Casimir predictions. Optical systems offer easier scalability than superconducting circuits. In Physical Review Letters in 1998, theory including corrections up to order alpha cubed, 3 loops in quantum electrodynamics, predicts 41,100 megahertz. Agreement to 1 part in 1,000. These measurements test vacuum polarization effects, nuclear structure contributions, and recoil corrections with unprecedented precision. Discrepancies between theory and experiment would signal new physics beyond quantum electrodynamics. None found. Signatures of phonon pair production at the horizon. The experiments, reported in multiple papers, including one in Physical Review Letters, confirmed the thermal spectrum predicted by Hawking's calculation applied to sound waves. Critics questioned whether classical water waves truly test quantum Hawking radiation, but the mathematical equivalence is strong enough that most physicists accept these as meaningful analog tests. Jeff Steinhauer's 2015 experiment with Bose-Einstein condensates went further by measuring quantum correlations directly. Using atoms cooled to below 1 microkelvin, he created a flowing condensate with a region where the flow speed exceeds the speed of sound in the condensate. Density fluctuations in the condensate act as phonons. At the acoustic horizon, phonon pairs form. Steinhauer measured correlations between density variations inside and outside the horizon using absorption imaging. The correlation pattern showed the characteristic spatial structure predicted for entangled Hawking pairs, published in Nature Physics. This experiment required 6 full days of data collection and sophisticated noise reduction to extract the signal. The Unruh effect entered experimental territory in 2019, when Morgan Lynch analyzed CERN's NA63 channeling experiments. Electrons channeled through aligned silicon crystals oscillate transversely as they follow channels between atomic planes. The oscillation frequency reaches 10 to the 22 Hz, acceleration 10 to the 21 meters per second squared, Unruh temperature 400 Kelvin. Lynch calculated the radiation spectrum these electrons should emit if the Unruh effect is real. The spectrum includes thermal corrections at the Unruh temperature. Lynch compared this to measured data from NA63 on quantum radiation reaction in crystals. The fit was excellent, reduced chi-squared below 1 standard deviation. This represents the first claimed experimental observation of the Unruh effect using real particles, not analogs. Published in Physics Letters B and later refined in European Physical Journal C in 2024, the result remains under scrutiny. Some physicists argue that radiation reaction can explain the data without invoking Unruh thermalization. Others accept Lynch's interpretation as evidence supporting Unruh's prediction. Using Berry's phase, a geometric phase acquired by quantum states, researchers showed that detection might be possible at lower accelerations than naively expected, potentially making the effect observable in laser matter interactions at intensities achievable in 10 years. Published in Physical Review Letters, the paper suggested accelerating atoms through strong laser fields and measuring phase shifts in their wave functions. The phase shift encodes information about the thermal bath the atom experiences. Experiments have not yet implemented this proposal. Using adiabatic renormalization in curved space-time, they found that vacuum energy acquires a term proportional to h squared, the square of the Hubble parameter. This introduces mild time variation. At present, the contribution is small, but in the early universe it could have been significant. The running vacuum model predicts an effective dark energy without introducing new fields like quintessence. Observational tests using type Ia supernovae and cosmic microwave background data show the model provides fits to data comparable to or better than the standard lambda CDM model. Whether this resolves the cosmological constant problem depends on whether the framework correctly captures quantum field theory corrections in curved spacetime. Debate continues. In 2024, a preprint on Archive proposed that vacuum energy at Planck scales might cancel due to quantum gravity effects. Specifically, that transplanckian modes don't contribute because spacetime itself becomes discrete at the Planck scale. If spacetime has a minimum length scale set by Planck length, 1.6 times 10 to the negative 35 meters, then field modes with wavelengths shorter than this don't exist. The cutoff becomes physical, not arbitrary. Calculating vacuum energy with this cutoff still gives large values, but order 120 orders of magnitude, smaller than the naive Planck scale calculation. This brings the mismatch down to 60 orders of magnitude, still enormous, but marginally less catastrophic. The idea requires a theory of quantum gravity to flesh out. String theory, loop quantum gravity, and causal set theory all suggest spacetime discreteness, but none provide definitive predictions for vacuum energy. This implies a fundamental limit on the information content of spacetime. Applying this to vacuum energy, they argued that correlations between ultraviolet and infrared cutoffs reduce the effective vacuum energy density to values consistent with observations. Published in Physical Review D, their calculation gives a cosmological constant within 1 order of magnitude of the measured value. If correct, this would solve the cosmological constant problem through quantum gravity considerations. Critics point out that the bound relies on assumptions about entropy that may not hold in quantum gravity. At these intensities, electric field strengths approach the Schwinger limit, 1.3 times 10 to the 18 volts per meter, where vacuum breaks down through spontaneous electron-positron pair creation. Detecting such pair production would confirm that the vacuum can be torn apart by strong fields, another prediction of quantum electrodynamics. As of 2025, no experiment has reached the Schwinger limit. Petawatt lasers get close but fall short by factors of 10 to 100. Measurements of one electron affect measurements of the other, even if they're separated by large distances. This spooky action at a distance, Einstein's phrase, originates in the vacuum field mediating interactions. Recent experiments in quantum communication exploit entanglement for secure information transmission. Photon pairs created in spontaneous parametric down conversion, a process where a pump photon splits into two lower energy photons. Through a crystal's nonlinearity, exhibit entanglement. These pairs have been transmitted over distances exceeding 1,000 kilometers through optical fibers and through free space to satellites, demonstrating that vacuum-mediated entanglement persists across macroscopic scales. This energy has measurable effects, pushing metal plates together, shifting atomic energy levels, creating particles when boundaries move or observers accelerate, and perhaps filling the universe as dark energy driving accelerated expansion. Yet the vacuum's energy density is fantastically smaller than particle physics predicts. The universe exists in a state balanced on a knife edge. Vacuum energy just large enough to accelerate expansion, just small enough not to prevent structure formation. Whether this balance arises from unknown symmetries, anthropic selection in a multiverse, or new physics beyond the standard model remains an open question. That's equivalent to roughly 6 hydrogen atoms per cubic meter of space. Not much, yet multiply by the volume of the observable universe, 4 times 10 to the 80 cubic meters, and you get 2.4 times 10 to the 54 kilograms of dark energy, more than all the ordinary matter in the observable universe by a factor of 2. The vacuum, despite being almost nothing, dominates the universe's mass energy budget. The story ends with a piece of data from 2023. Planck satellite final results, analyzing cosmic microwave background radiation in exquisite detail, confirmed dark energy density to 3 significant figures. Omega lambda equals 0.684 plus or minus 0.010. This parameter represents the fraction of the universe's total energy content in vacuum energy. 68.4% of everything is vacuum. Matter, both ordinary and dark, accounts for 31.6%. The void isn't just refusing to be empty, it's running the show, and we still don't know why.